Good morning. Now I'm going to give you a revision on lecture 5, which is circular motion, and somehow in our syllabus most of the time we will try to focus on uniform circular motion. Okay, first you must understand what is uniform circular motion, where of course you know that it's a circular motion and all the linear speed or linear speed here, or sometimes we name it tangential speed, is a constant, which means all the time v1, v2, v3, v4 is still same as v. As a result, then in terms of speed, there is no any change, but somehow if in terms of velocity, if we consider velocity, since there's a change of direction, then actually there is a acceleration. And through the experiment and also through some mathematics steps, we know that all the time at every moment here, let's say, there is an acceleration, there is an acceleration, there is an acceleration here, and we name it AC. The magnitude is v squared over r, and this one the direction is always towards the center, and that is something we need to know. And this AC equal to v squared over r is only for circular motion, which means that whenever they say the car make a turn such a way and make a circular motion. So in order to answer or understand this question, we still need to use the Newton's law, whereby still the same thing, sigma F equal to ma, but somehow if it's a circular motion, then we can say it's mac. Let me give you a simple example. If let's say this is a horizontal surface, and somehow we use a string, let's say, and there's a ball attached at the end, and we make a circular motion. But as I say, it's a horizontal circle, which means it's not vertical circle. Then you know that always there's a tension here. So let us cut it into two parts. So basically you need to consider this part only, whereby we still use the same thing from sigma F equal to mac. The AC because why? It is in circular motion. So this M, in this case, there is only the force that applied on the ball is only tension. So tension equal mac equal mv squared over r. That is something that we need to consider, which is such a way, a simple example. On the other hand, if let's say there is a, right now we make a circular motion, okay, make a circle, the ball, let's say I play it like this, then the ball had experienced a circular motion vertically. If it's vertically, then a little bit tough. And in our syllabus, most of the time, we will consider at the top point or top position and also at the bottom position. So let me go through one by one. Again, we still use the same thing, which is sigma F equal mac. And at the top part or top position here is something like this. At this moment, of course, there's a string, so there's a tension to bring it downward. On the other hand, this ball itself has another mg. Bear in mind, this is a vertical circle, and as a result, the acceleration is pointing downward into the towards the center. So sigma F equal to mac. In this case, maybe I can put it in the vector form like this, such a way. Then I consider the downward is positive, then T plus mg equal mv squared over r. And T equal, in this case, which means that T equal mv squared r minus g. So you can see that in order to get a positive, since always we say that T must greater than 0. Why? If T less than 0, which means no tension, which means that actually you cannot make a circle. And in order to get the T that is greater than 0, which means v squared over r must always greater than G, at least same as G, greater or equal to G. Therefore, it depends. So that is quite logical. If let's say you have the longer wire, then you must apply a higher speed. If you do not, for the same speed, you must use a shorter wire or shorter string in order to then move in a smooth vertical circle, such a way. And basically, as I say, circular motion is part of Newton's law, whereas we can use Newton's law to try to solve a lot of the question regarding or about circular motion. One of the example is the next one which I will give you now. Let's say conical pendulum. There is a surface here. Let's say it's a ceiling or whatever, which is fixed, and this wire or this string is fixed. So you make a circular motion like this. So you know that actually you make a circular motion like this, such a way, which means that it's something like this. Then, in order to investigate this question, first, there is always tension here. Second, as a result, it has AC here. Somehow, there is energy to support it. From here, you know that the final movement is to the right. No vertical movement, which means that definitely there's a vertical component here to cancel the mg. And coincidentally, there's a tension here, so you know that if here is theta, then maybe I use another color. If we make a theta respective to the vertical component, which means that here is also theta. Hence, this component, the vertical component is t cos theta. On the other hand, there is a horizontal component which is t sin theta. And since we know that the final movement is to the right or inward, there is no vertical movement, which means sigma Fy equals 0. Sigma Fy acted on this ball or pendulum equals 0. So t cos theta minus mg equals 0. T cos theta equal mg. On the other hand, sigma fx is equal to mac. Hence, there's only one component, which is t sin theta. Let me put it. T sin theta equal mv squared over r. So let's say this is equation 2. So equation 2 divided by equation 1 to get tangent theta equal 2 divided by 1, so it's v squared over rg. So maybe you will ask me, is there a formula that I can use all the time? Again, it's similar to chapter 4. We cannot consider this is a formula, but we must start from scratch. First, apply the Newton's second law and try to imagine all those which one give you the final movement, and then we substitute accordingly. So all this one normally must are reserved for all these equations. If you suddenly jump to here by just memorizing the formula, mostly you lost marks. A lot of examples here, and somehow it depends on the how do you do that. If let's say I say for a car system, a car, let's say, if you make a horizontal circle, then we may say that the frictional force supply or contribute to the AC. So when the car make a, let's say this is the cross section area, the top view here, and make a circular motion here, then we say that the FFR acted on the wire, on the tire, contribute to the circular motion. So FFR equal mv squared over r. On the other hand, this FFR is mu. Since it is moving, so it's mu k, no mu s. Fn equal mv squared over r. And mu k Fn, basically for the horizontal such like this, the car is moving like this, then we can say that mu k mg equal mv squared over r. Then can we solve it? Basically we can solve it. But somehow again I would like to tell you that, I would like to point out that there is no so-called the last formula for circular motion, but we need to know, we need to understand how do we connect it or relate it to the Newton's law. Next example. There is a bend curve at theta and the car is at here. So we make a circular motion such a way. So the first thing, you know that the final movement, the car is not sliding down, it's not sliding up. First thing. Second, the final movement is a circular motion, which means that there is an acceleration AC towards the center or inward. And for this case, we need to investigate furthermore. There is mg here. There is Fn here. Since just now I said that there is no vertical component or vertical movement, which means that sigma Fy is equal to 0. And this sigma Fy equal to 0, which means that definitely there is a component, vertical component to cancel the mg. And so, which means that you need to cut it here. So this is Fn y. On the other hand, you resolve it here also, there is Fn x. Therefore, then how? Maybe you ask, how do I get whether this is theta or here is theta? Let me give you some explanation here. I make it bigger. Here is theta. This is the object. So maybe I can put it as phi, whereas phi equal 90 minus theta. So since that here is 90 degree also, so here definitely is theta, and this is a component of mg here. On the other hand, you put such a way, this is the component of Fn, and here is Fny. So if you compare here, it's theta, which means here is also theta. I repeat again. If start from here is theta, and maybe here I put it as phi, where phi is 90 minus theta. So since this component is 90 degree, has a 90 degree here, which means at last here is theta. That's why I always say if we resolve the mg, this part is mg cos theta. And if since here is theta, then we can put the theta here. Hence, Fny minus mg equals 0. Fny equal mg, where Fmy is actually Fn cos theta equal mg. I would like to repeat again. It's not a formula, but you need to start from the Newton's second law. Either the force is in equilibrium or there's an acceleration. That's all. And for the x component, horizontal component, since there's only Fnx, so this Fnx contribute to the mv squared over r, and Fnx in this case is Fn sine theta equal to mv squared over r. My next question is, what is the value of Fn? Of course, you can find out accordingly, and up to you whether you want to find out, or else maybe you can also use some mathematical skill or equation or operation to cancel the effect of Fn. So let's say I put it equation 2 divided by equation 1, then tangent theta equal to v squared over rg. It looks like similar to the certain question, which is just now example that I gave just now. Actually, there's something, a formula similar to this one, but somehow, as I said, I won't encourage you to memorize it, but by using the Newton's law. And for uniform circular motion, actually there are two types. One is for circular motion, there are two types. One is uniform, one is non-uniform. I would like to remind you all. For the uniform, which means that all the time the speed is the same. But somehow, if a non-uniform, it may be different. So maybe you ask, for a system, let's say, this is a ball. As I say, basically, if it's a ball, keep rotating. The whole body keep rotating, then it involves rotational motion. On the other hand, if they say there is something here, stick to the point, stick to the surface or the surface here, yes, or the ground, so-called the ground, then it experiences a circular motion. Therefore, if this object is rotating at a fixed omega, angular velocity, hence the v is also fixed. On the other hand, if this one is rotating at a fixed alpha or even different alpha, keep changing, let's say, the movement keep changing, maybe it's a positive alpha, negative alpha, or change here and there, then maybe fixed or not fixed, but not equal 0, then the v is also not fixed. If your v is not fixed, which means that it's no longer uniform circular motion. You can still use this formula mv squared over r, but this v is the v at that particular instant. It's not the v for the whole system, but it's just the v of the object at that particular instance. And the one, for more information, I will discuss it in the rotational motion part. And right now, I would like to give example on the another one, which is a common question: roller coaster versus Ferris wheel. When we talk about Ferris wheel, normally you can try to imagine so-called the Eye of Malaysia. Right now, it is located at Malacca. So Eye of Malaysia basically is also the same thing. You make a circle, that is vertical circle. This is a vertical circle, and somehow all the time the passenger is sitting upright. Okay? There's no upside down, but it's all the time sitting upright. So maybe I would like to ask you, what is the force acted, or what is the force applied on this human or this guy? Then basically in our syllabus we still cover two parts. One is the top part, one is the bottom part. And we try to see what is the difference if you compare to the vertical circle you applied for a ball just now. Is there any difference? Let's see. And here, first, the force acted on this guy, of course we have the normal force. Next, the mg itself. As a result, the AC is going downward. So we still use sigma F equal to ma, and in this case is basically is mg minus Fn equal mv squared over r. Then we rearrange it. Fn is mg minus mv squared over r. So what happens if your v is too large? Since we also say that Fn must always greater or equal to 0. So if from this equation you see that when v squared over r is greater than g, Fn smaller than 0. And when Fn is smaller than 0, you can imagine that, which means no normal force in this case, so that basically theoretically this one fly away. Okay, there's no longer it can stay in this box. Somehow we try to consider this is for the top part. For the bottom part, when the guys are at the bottom of the Ferris wheel, such a way, so at this one, still sitting upright, there is Fn, there is mg, and as a result, there's a vertical acceleration. And again, we use sigma F equal to ma. Sigma F equal to ma. Then we use Fn minus mg equal mv squared over r. Hence, Fn equal mg plus mv squared over r. So, mg is positive, mv squared per r also positive. So, all the time Fn is positive. So, there is no limit unless you feel uncomfortable because due to the very fast speed. But in terms of physics or mathematics here, it is fine, no problem. So the next example I will give you is on the roller coaster. Let's say a roller coaster is designed in such a way where this is a circle, vertical circle. So let's say I make it property. At the top part, what is the force applied on the body? And at the top part, which means that right now the human is sitting upside down like this. So the Fn is inward, downward. On the other hand, mg is also downward. As a result, AC is downward. So for this case, still the same, sigma F equal to ma. Then right now become mg plus Fn. Therefore, Fn equal to mv squared over r minus mg. And from here again, Fn must greater than 0, which means that v squared over r must greater k. Then only correct. So if you compare to the Ferris wheel, roller coaster and Ferris wheel, the concept is the same. We still use the circular motion theory and also the Newton's second law, but somehow when we investigate, it gives you a different formula. Again, that's why I said that in the circular motion, we never memorize the final formula, which is useless. Again, for the bottom part here, for the roller coaster, it's still the same thing, which means that people sitting upright. Then this is the Fn, mg downward, as a result AC upward. So we can still use the same formula, exactly same as the Ferris wheel just now. So basically, this is what I would like to discuss with you today. Thank you.